Alright guys, let's go crazy. Here I've got some solid argon in my little phases of matter simulator, and I'm just going to add some heat to it and let's see what happens. So we know that those particles should start moving faster and faster, and at some point they'll become a liquid. So I think we've got that now. You can see they're starting to not stick to each other as well, and they're starting to move around. So let's add some more heat to this. They start moving faster and faster and faster. You can see that one is going crazy in there, and now they've reached the point where they're moving so fast they can't stick together. Well, let's keep going. And let's just keep going. And let's see how far this will go. So what we've done here, and we can think this is an actual physical situation that we could talk about, is that we've taken this solid sample of argon, and then we heat it up till it becomes a liquid, and then we heat it up until it becomes a gas. And now we're just going to keep heating that gas up and keep heating that gas up. And those particles keep moving faster and faster and faster and slamming into each other harder and harder and harder. And it just keeps going and keeps going. And we can run this simulation into the ground, but the simulation is never going to show us what happens next. Because what happens next is frankly kind of incredible. We'll get this up to about 1,000 kelvins, and you can see that the atoms will be moving really, really, really fast. But this poor simulator can't really tell us what comes next. Because once these start moving fast enough, once you've heated up a gas enough, it turns into a new state of matter that we call a plasma. And a plasma is what happens when these atoms are moving so fast and hitting against each other so hard, and there's so much energy within that atom that the atom itself breaks apart. Now I know I told you earlier atoms don't really break apart, right? But this is just a useful model for us to use. Atoms in fact do have different parts, and they can be broken apart. It's just for right now, all the chemistry that we're learning, we can learn knowing or thinking of an atom as something that can't be broken down. But when you heat a gas up far enough and you give these atoms enough energy, the atom itself does break down into different parts. And these different parts have a property called electrical charge. And so when the atom breaks down, you have all these so-called charged particles moving around, and these particles respond to like magnets and electric currents and electric fields, which means, well, for a gas it means nothing. You can hold a magnet next to a gas and it's not going to do anything, but if you hold a magnet next to a plasma, the plasma reacts to it. So this gas, by heating it up, the atoms actually break down and it turns into a state of matter called plasma. Now there are some places where you can see plasma on Earth, and a lightning strike, that blue bolt that you see through the sky, is actually a plasma of the air. If you're ever lucky enough to see the northern lights, or at least see a video of the northern lights, so the auroras, that happens when particles from the sun strike the upper atmosphere and actually turn the air into a plasma, and it makes these beautiful colors. Fluorescent lights inside those glass tubes that you see, a plasma forms inside those. Neon lights as well, and in plasma TVs there's some use for those as well. But plasmas are not all that common on Earth. Even though they're not common on Earth, plasma is the most common state of matter in the entire universe. That is, more of the universe is made of plasma than anything else, and here's why. The sun is just a gigantic ball of plasma, and inside the sun there are all these electric and magnetic fields that cause the plasma to move around, and we can actually take a look at some of those motions. And so I'll just run this YouTube video for a second, and you can see that motion. See all of that there, those sort of streamers and everything you see coming off the edge of the sun, that's plasma reacting to the magnetic fields. So again, this plasma, it's a different state of matter, and it responds to electricity and to magnetism in ways that other states of matter don't. And it's very, very hot. You don't get plasmas at temperatures that you see every day. In order for a plasma to form, you have to have extremely high temperatures, such as the ones in the sun. And that's sort of the skinny on plasmas.